Hello, good evening, everyone. My name is Scott Grizzard from the University of South Florida. This is Calculus, Class 4A, the definition of the derivative. So today we're going to be talking about the derivative, what all this limit stuff has been building toward. You know, the whole point of the first stuff of the last 3 weeks has been to get to this point. So it's exciting. As usual, there is Discord. There is Twitch chat over there where you may ask questions. But remember, that's public. You may ask questions in Discord and the chat channel, and that will be reserved to our class. The test is on Saturday. Ooh, test. So this is hopefully I will get everything done tonight, and this will be the last lecture whose material goes on the test. Of course, there's a problem set. And then you have all sorts of study materials like the bootleg, the study guide. I will make an announcement later about every little thing that you have, and of course the peer leading guide. There's peer leading on Friday. The stuff that we talk about on Thursday, where we will actually do the derivative. We will actually prove the product rule next on Thursday. That stuff is not on the test per se, but it's usually similar to a problem that shows up on the test. So if you want to kind of get a little leg up, the stuff that we will be doing Thursday at 7 p.m. Will not be on the calculus test proper, but it's kind of a good idea to watch the video because it kind of goes into some of those proofs. Okay, so without further ado, last time we talked about continuity. Let me go ahead and pull that up. Okay, so last time we went over continuity, we did the intermediate value theorem, which I used today in my stuff for my math, which was kind of exciting. Graduate algebra, trying to get that PhD, graduate algebra class, needed IVT to solve a problem, which is fun. Today, of course, we're going to be talking about the derivative. So we've already done this a couple times. So in peer leading, you had a packet that talked about velocity. Today, you've got another packet that talks about velocity and all of those things. And that's the best intuition for the derivative. It's kind of the original application. But it's done to death, right? We've done it. If it's the only one that you get that one. If that's the only kind of example of intuition that you get that one. So tonight what we're going to do is another one. We're going to talk about some of the economic ones because they're slightly different and they make... it depends. Some people find them more enlightening. Some people like the velocity one. By all means, if that's you, go for it. But some people like the economic ones a little bit better. And if that's the case, then tonight's for you. So we'll go over marginal cost and things like that. And then we'll do the definition of the derivative. There are two of them. We'll do some examples on how to find the derivatives based on the definition. And then we'll talk about some things, how things can fail to be differentiable. And then we'll do the notations for the derivative. There are a ton of notations for the derivative. And you just have to know them all. Well, you don't have to know them all. We're not going to do Newton's dot notation, but there's a lot of different notations for the derivative, and you need to know it. Now, and then we'll talk about higher derivatives briefly. Now, the notes for tonight, if you looked if you looked on the, that's wrong. If you looked on the Canvas site, as I said, that's wrong. That should be the other packet. But if you look on the Canvas site, the notes here are not on a PDF. They're just on here. It's got a nice little moving picture, so I wanted this here. So this is kind of the thing. And we'll do that. There's also these two videos, and these are both very good. I highly recommend thinking about them, just checking them out as kind of a supplement for this class. Okay. And people are nervous about the test and all of those things. Okay. So let's get started. Let me make sure I've got this thing up for questions. I do. Let's shrink this. Not that. I need that. This one. Okay. So now I can see what's going on. So as I said last time we did do it, they were doing the derivatives. So we've done this velocity thing already, but let's look at a different problem. Let's look at Thanksgiving dinner. Okay, so suppose I'm eating by myself, right? I'm alone. I'm a loser. I have no friends. And actually, or it's COVID, and I'm afraid about infecting my grandparents and stuff. So I stay home for Thanksgiving, or I eat by myself. Now, if it's just me eating Thanksgiving dinner, if I'm eating Thanksgiving dinner by myself, I'm gonna like go out to a restaurant, or I'll order some, Uber Eats or something like that, and it's going to cost me, with a bottle of wine or three, it'll cost me like $50, right? So one person, if I'm just doing one person, it's like circa $50, to 75 depending on the wine bill, you know. So this is me. I order a turkey. I order like part of a turkey, and I don't cook anything. I just order on Uber Eats. Now, if it's two people, right, I'm going to spend like $125. There's two of us. We'll split the bottle of wine. Because there's two of us, because it's two of us, we're a little bit less sad. Ish, 125, maybe $100 for the two of us. Because we order, but I'll go pick it up if it's two of us, because I don't want to, maybe tip as much. Whatever. And that's so total about $50 a person. Maybe these are a little unrealistic. Maybe I'll do $100 for just myself. And then for this, we might go all the way up to $150 for this if it's two of us. So that'd be $75 a person. For 3, 4, once we start getting into 4 people, I'm cooking a turkey, right? So it's going to run us, about $200. Which is about $50 a person. And what's the point? Well, when I start getting down here to, 20 people. So if I'm inviting 20 people for Thanksgiving dinner, right, how much are we spending per person? Well, $20, right? I mean, it's a lot of money. Okay? But it's, we're spending a lot less per person because, I'm frying a couple turkeys. I'm, doing a whole bunch of other things. We can maybe get away with, for 20 people at $20 a piece, do a little math there. So $50 a person. Maybe we're doing $30 a person. Maybe we'll spend, $40 a person. Oh, $30 a person. So we're going to spend like $600. Okay? But notice what happens to the cost, right? If I'm cooking for 3 people and my cousin who's coming invites some significant other, that's a really big imposition. But if I'm cooking for 20 people already, one extra person shows up, I go grab another box of wine from the basement, and I just bring it up, right? I mean, it's not really that large of a cost. Okay? So how do we feel about this? The cost of the margin the next person changes. How do we feel about that idea? 1 to 5. Okay. I'm getting of 14 viewers, one person has decided to actually share their opinion. Okay, a couple more. Excellent. And some people are actually on, text week. People show up. That's new. Yes. I like it. Okay. So there's this idea that my total cost right? My total cost looks something like this. It's always increasing, right? But around 20 people, it's at 600. At one person here, right? At 2 people, it's at 150. At one person, it's kind of at not drawn to scale, obviously. But right, I go from 100 to 150. So my marginal cost, my cost at the margin of adding the second person, my cost at the margin of person 2, right, is the cost C of, so let's see. So let's see it be the total cost. Now, my marginal cost, which is different than my average cost. What's my marginal cost? If I'm already paying $100, if I'm already doing Thanksgiving for one, what is the cost of the second person? Okay. This right here would be average cost, which is different than marginal cost. So what I'm going to do is I'm going to ask myself, what is the cost of the next person? Okay, so I've got C of person 2. So I've got C of the first person, I'm sorry, of the 2 people, minus C of the second person divided by the additional number of people, right? Which is the change in people, which in this case is 1. And that comes out to be $50, right? It cost me $50 to add another person once I was already adding that many. How do we feel about that 1 to 5? All right. So let's suppose up here at 19 people, it cost 500 and let's make it so that it's not going to go significantly. $585. So what is the marginal cost at 19 people? So what is the marginal cost of person 20? So the marginal cost of person 20 is what? Okay. Well, how am I going to do that? Well, what I'm going to do is I'm going to take the cost of person 20 I'm going to subtract the cost of person 19. I'm going to do that over the change in people, which is 20 minus 19, or 1. That's going to give me the number, right? So it's, 600 minus 585. It's going to be 15 over 1. So it only cost me $15. I'm sorry, 85. So 15. So it only cost me $15 to add the 20th person, right? That's okay. I can't do basic math either. So how do we feel about that? This idea of marginal cost is getting lower. All right. Okay. So now, let's look at another example. All right. So let's say that Exxon, who's, going downhill, let's say that a company produces gasoline. And let's give this a nice little number. Let's say it's the cube root of C of the cost in terms of quantity equals the cube root of Q plus 1,000, where C of Q is in $1,000 increments. And Q is in units of 100 gallons. It's not actually that. What would be the let's do Q as in gallons. So we'll do C of Q is just in dollars. This is just totally unrealistic. Is in dollars. Actually, it's not that. So let's make this a little bit more realistic. It's going to be plus 10 million. There we go. Now it's more realistic, right? Okay. So what's the marginal cost of making that kind of first gallon of gasoline? Right. It's expensive. It's expensive to make that first gallon of gasoline, right? It costs $10 million in fixed costs, right? I got to pay that no matter how much gasoline I make, right? So this thing is going to be like, let's even graph it on Desmos. And notice that the amount that we're going to spend always goes up. So if I want to make more gasoline, right? It always costs me more to make more gas. All right. So, but if I want to look at this, let me make this do this. Plus $10 million here. All right. So if I want to look at this, let's just say the $10 million is there without actually putting it there. So if I want to look at this as a graph, it's going to look something like this. Of course, there's an adjustment here, right? There's an extra $10 million tacked onto this, right? But let's forget about the fixed cost for a moment, right? So the cost always increases. But notice here how the quantity when I produce more and more, the additional cost gets less and less and less, right? So this is this idea of diminishing marginal cost. Okay. So let's look at this. How are we going to do this, right? I'm going to do, what is the cost? So what is the marginal cost of 25? So what is the marginal cost of the 25th unit of gasoline? So that's our question. What is the marginal cost of the 25th unit? Of the 25th gallon. Okay. Well, let's do it. So the marginal cost of 25 is about, let's see, let's do the marginal cost of producing the 25th gallon, which would be the cube root of 25 plus 10 million, right? That's million, minus the cost of producing the 24th gallon, right? So the cost of producing 25 gallons minus the cost of producing 24 gallons. Of course, totally unrealistic. How do we feel about that kind of idea? So I've just got y2 minus y1 over x1 minus x2. So when I do this thing right here, I'm going to wind up with the cube root of 25 minus, now notice that this 10 million and that 10 million are going to cancel, right? I've got minus 10 mil minus the cube root of 24 minus 10 mil again over 25 minus 24, which is just 1. And these fixed costs go away. And I'm left with the cube root of 25 minus the cube root of 24. All right, so if I plug that over into my calculator here, which I should have had up from the get-go. So if I plug that into my calculator here, I wind up with the cube root of 25, which is approximately, let's see, how do you do whatever? We're going to do, oops, I don't want 0 to the whatever. How do you clear? There it is. We want the 25 to the 1 over 3. That helped. We'll just do 25 to the 1 over 3. We'll ask Google here. Minus 24 to the 1/3. And we wind up with some kind of answer that it doesn't give me because I put an equal sign there. And we wind up with an answer of about 0. So it cost about 4 cents to make that extra gallon of gasoline. Thanks. And I messed up the thing. Sorry. So we wind up with this approximately being 0.0395, blah, 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 blah. And let's see. And that is, you are correct. I needed a plus there, not a minus. Okay. So that's about the marginal cost of that 25th gallon of gasoline. Okay? But is there anything special about doing units in gallons? Is there anything really special about that? Okay, and there's not really, right? I mean, I could have done gasoline by the 2 gallon. I could have done gasoline by the liter. You know, if we were in Europe, we'd do gasoline by the liter, or in Canada. You know, there are countries that, you know, use the metric system, and then there are countries that have put a man on the moon. But, you know, we could have done that. But there's nothing really special about it, right? If I did this by the half gallon, what would I get? So let's do it by the half gallon. Or I could have done it by the quart. Okay? But this is by the gallon. Let's do it by the half gallon. Okay? So we've got the marginal cost of 25 done by the half gallon would be the cube root of 25 plus the 10 mil, which is going to go away, right? Minus the cube root of 24.5 plus the 10 mil, which is going to go away, over 25 minus 24.5, which is going to equal, right? You go away, which is the cube root of 25 minus the cube root of 24.5 over 0.5. Okay, so before my answer was this, let me just paste that answer in there. So this is my answer for up here. I'm not sure if you could see that. Yeah, so that was my answer for that. Now I'm going to do a little change here. I'm just going to do this. I'm going to put a 24.5 here. And then I'm going to divide the whole thing by 0.5. Or I'm going to multiply it by 2, which would be the same thing. All right. And I get a slightly different answer. Not really different. But I do get something slightly different. And I could go again and do it by the quart. If we wanted to do it by the quart, plus something that's going to cancel, plus something that's going to cancel, and I run the number here. Let's put it in here. And I get another slightly different answer. Oops. So how do we feel about that 1 to 5? So before, when I was talking about the marginal cost of adding a person to Thanksgiving dinner, right? It doesn't really make sense for me to add half a person, unless it's my niece who, eats like half a person. Okay, I guess I could do that. And doesn't drink wine. She kind of skews everything out. But, it's really not, there's nothing really special in this thing about measuring by the gallon. I could have done it by the quart and all of these other things. But these numbers are tending to something, aren't they? Right? I went from 0.0395 to 0.0392 to 0.0391. If I just said 0.039 and said close enough for government work, that would be a good approximation of what I'm doing. But I could do something even better. If I want something that's units independent, okay, for marginal cost, and I say units independent because it's not actually, it's still in price per gallon. This is still in dollars per gallon. Right? Even though I'm doing it by the quart, the equation, the number is still dollars per gallon. Right? That was the point. When I did it by the half gallon, I ended up, dividing by 0.5, which is multiplied by 2. When I did it by the quarter gallon or by the quart, I divided by 0.25, which is the same as multiplying by 4. So if I want something that's, maybe not units is the thing. If I want something that's distance from, right, I'm better off taking a limit, because that would give me the kind of thing it went to. So what I'm going to do is I'm going to let this margin go to 0. So here, if I want something that is margin independent, maybe we should do that. Margin size independent. I let the margin of x go to 0. And let's look at what happens if I do that. Okay? So let's take this again. I've got the limit, the marginal cost in terms of quantity would equal then the limit as the change goes to 0 of cost in terms of quantity plus h minus C of Q over H. Or I could say the limit as MC of Q equals the limit as Q, I want to say the margin, and the margin here is 1, right? So I'm just going to leave that like it is. All right, how do we feel about that 1 to 5? So I want this kind of this kind of independent thing. It doesn't really matter how much we're changing by. I'm just going to go. Okay. Someone's asking, what is a limit? How come I write the equation into Google? Because all I wanted was a quick answer. Okay, so the point is that the change is going, yeah, I think they are trolling. Okay, there's good justification for leaving the chat as emote, but I'm not. So yes. Okay. So okay. So there we go. So I've got this idea of the limit as h goes to 0, which is what we've been talking about the whole time, right? This arbitrarily small thing, okay? This arbitrarily small number. And so what I'm going to do here is I'm going to compute it. So, and I can actually come up with a curve for this marginal cost. Okay? So let's do that. If I use the formula here, I'm going to wind up with the marginal cost of Q for this particular one is the limit as h goes to 0. Now, cost of Q plus h. I could actually do this with another formula too. What was it? Q brute. So this is the same as the limit as we'll just say t goes to x, or t goes to q, of c of q minus c of t all over q minus t. So we'll do it this way first. So we'll have the limit as t goes to q, right? The second goes to the first. Now, the cost of q is the cube root of q minus the cost of t over q minus t. Okay. Now, I don't know how many of you remember this, but there is a formula called the difference of cubes. This right here, this q, and again, this is a little algebra that I don't expect you to know off the top of your head. As a matter of fact, every time I use it, I have to kind of rederive it for myself because I never remember what it is. But this q here, I could think of this q as the cube root of q cubed. And I've done this a few times. And what I wind up with is the limit as t goes to q. Now, the formula that you could remember is the a cubed minus b cubed. Does anyone remember the difference of cubes? Anyone remember the formula? The difference of cubes. Do we remember it? Nope. Okay. The difference of cube formula, no. I don't remember it either until I need it, right? It's a minus b times the quantity a squared plus ab plus b squared. And I have to, as I said, I have to rederive it every time I do it. I know it's a minus b goes into it, and then to remember what the other term is, I have to rederive it. Okay. So I don't expect you to know it for the test, but I'm saying we can use this trick here. So the difference of cubes here, I'm going to wind up with the limit of q minus the cube root of t over, and then I'm going to use this little difference of cube formulas here, where a equals the cube root of q, and b equals the cube root of t. I'm going to wind up with the following. I'll wind up on the bottom, I'll wind up with q. I'm going to write q to the 1/3, just because it's faster. Minus t to the 1/3. Times the quantity a to, so q to the 2/3. plus q to the 1/3 t to the 1/3 plus what is this last one here? T to the 2/3. Oh my goodness, that is ugly. Yuck. Ugh. It's like not aesthetically pleasing whatsoever, is it? But these two terms cancel. Now, but something kind of interesting happens here. Now I've got the limit as t goes to q of 1 over this ugly expression. Okay, well, this is a sort of like a rational function. I mean, it's got some radicals in here, but it's defined if you know, things are away from 0. Right? And these are, right? I'm not near 0. So what I'm going to do is I'm just going to directly sub q for t. And I wind up with 1 over q to the 2/3 plus q to the 1/3, q to the 1/3, plus q to the 2/3. Well, these two terms add up to be, you know, I'm taking q to the 1/3 and multiplying it by q to the 1/3. I add the exponents. And this becomes 2 to the q 2/3. And so what I wind up with is 1 over 3 times q to the 2 over 3. And look at this compared to this. And that's kind of beautiful, right? All of this crap that was here went away. It came out to some nice little expression. Now, the algebra is brutal because it requires this trick that I'm not expecting you to remember, right? I Googled it. Okay, I go on Google, I go to the Cliffs Notes site, and I wind up with the difference of cubes. By the way, it's easy to remember the sum of cubes. You just switch these two signals, by the way. How do we feel about that 1 to 5? I went for something that was ugly, threw something uglier, and wound up with something relatively pretty. And that's kind of interesting. So, ugly. Really ugly. Right? This right here is ugly. Is like a modern art masterpiece ugly. Right? That's really ugly. This is kind of beautiful. So, this idea, yeah, what happened to the t? Well, I directly subbed in, right? I was doing t to q. So I subbed in q for all the t's. And I wind up with 1 over q to the 2/3 plus q to the 1/3, q to the 1/3 plus q to the 2/3. The numerator canceled out with this piece, and I wind up with something rather pretty. And that's kind of nice. And this will give me the answer. So if I throw in, let's do marginal cost of 25 again. All right, let's throw that one into our old Google. But now I've got a much simpler expression. So now my expression is 1 divided by the quantity 3 times 25 to the 2 over 3. And that might not look a lot nicer, but you know, it is. And I wind up with something that looks like this. Do, do, do. So now my marginal cost. Why isn't it moved? Oh, there it goes. So now my marginal cost is going to be 1 over 3 times 25 to the 2 over 3, which is about 0.038. We'll give it another 9, and we'll give it a 9 there. That was kind of where I was going, right? That's rather beautiful that it just comes out that way. So how do we feel about this 1 to 5 now? And if you have any questions, by all means, ask them. Let's see. Okay, and in the future, I guess we could tell trolls to get into Discord Discord chat. Okay. All right. Well, if we look at this equation again, we come back over here, and that actually gives us a slope of this tangent line at 25. Okay? So for this equation here, we actually wind up with a nice little slope of the tangent line there. And I wind up with this kind of idea, the C prime of 25 equaling about 0.04. But now I can also plug in this formula and get all the other marginal costs as well. All right. So that's another way of thinking about this intuition, right? The marginal cost of 25 equals the derivative equals the slope of the tangent line. And there's another interpretation of the derivative. That's not just velocity. Velocity's the best for most people. But as I said, velocity's been done to death in 3 packets now, or 2 packets. And I wanted to do something that's a little different. Okay. Now, when I talk about the marginal cost decreasing, let's throw this back into Desmos. Let's put 1 over 3x to the 2/3 into Desmos and see what comes up. Now, the book does something which is actually wrong. I mean, the book does... the book wants to put these things on the exact same... the book wants to put these things all on the exact same... oh, shoot. I want 25, don't I? So I need to shrink this. The book wants to put everything on the exact same graph, and that's actually technically incorrect. The graph of the derivative is a different graph. Its y's are interpreted differently. Okay, and I'll get into that in just a moment. But the graph of the derivative here is going to look something like this. And as you can see, when I do the graph of the derivative, right, here it is. Here, the value is 0.5 right there. Okay, let me zoom this in so you can see it. I don't know why it got zoomed out like that. Let's get rid of the ruler. So this is the marginal cost. And the marginal cost here this is wrong. There we go. All right. So the marginal cost here is 1 over 3 to the times x to the 2/3. So as you can see, near 0, this thing shoots off to infinity. You can't see my thing there at all. Okay, so when I'm near 0 here, it shoots off to infinity. But notice how it gets smaller and smaller. So as my, this has production of scale, right? As I get more and more quantity, the cost always increases. But the marginal cost, the cost of producing 1 more gallon of gasoline gets cheaper and cheaper and cheaper and cheaper, which fits our computations from before. How do we feel about that 1 to 5? So I've got 2 different graphs. All right. So the derivative, some notes on the derivative. One, the derivative is the slope of the tangent line. If you get nothing else from today, get that. That is the biggest idea. The second is that my units in output change, right? I'm talking about stuff at the margin. So the second is my output is really not in the same y space. In fact, it's in y prime space. If f takes things from x space to y space, f prime takes things from x space to dy over dx space. All right. And I want this to be, there's a trap here that you forget. So, for example, if x space is in miles, is in hours, and y space is in miles, dy over dx space is in miles per hour. And I want you to keep this in mind because it's a trap that you can run into. So it really doesn't make any sense to put these on the same graph like the book does. Now, as long as you're aware of this trap, it's actually fine. As long as you're aware that what you're looking at is 2 different things. So as long as you're aware of the trap, that's fine. But, your first time learning calculus, you're not really aware of the trap. So I want to make that little point. It's a subtle point, but I think you should have it in the back of your head. Okay. We did the example of the cube root of x. I actually meant to do the square root of x, and I did the cube root instead. Oh, well. Bad me. Let's do another example here. I'm not going to make that one. I don't know why I was thinking the cube root of x. I meant to do the square root of x because the algebra is simpler. And then I did the cube root of x. I probably did the cube root of x because that's the one on the bootleg. And it was just on my brain. Let's do another example. Let's let f of x equal 1 over x. And I want to do, so what I want to keep in mind are these two definitions. F prime of x equals the limit as t goes to x for fixed x. The limit as t goes to x of f of x minus f of t all over x minus t, which is the exact same thing as the limit as h goes to 0, f of x plus h minus f of x all over h. And I want to be able to use these interchangeably. And the reason why I want both is because some things are easier to do. So some things are easier to do with one definition, and some things are easier to do with the other. Okay. So let's do this one. Let's do f of x equals 1 over x. So I'm going to do f prime of x equals the limit as t goes to x, right, of 1 over x minus 1 over t over x minus t. Now, for comparison, I'm going to use the other one as well. F prime of x equals the limit as h goes to 0 of 1 over x plus h minus 1 over x all over h. Okay? Now, if I've got this one, what am I going to do? I'm going to do limit as t goes to x. I'm going to first cross multiply these, right? So I'm going to wind up with t over xt minus, I mean, cross multiply. I'm going to take them to common denominator. Excuse me. X over xt all over x minus t. And that's going to do the limit as t goes to x, okay, of t minus x all over xt all over x minus t. Okay, which is going to wind up being the limit as t goes to x of t minus x over xt times x minus t, which equals, now these things cancel, but I've got a -1 floating around. So let's put that -1 out here because I want this to be x minus t so that they cancel. The limit as t goes to x of those two cancels, and I wind up with -1 over xt, which equals, with a direct substitution, if what can't be true, if x does not equal 0, I wind up with the -1 over x times x, which equals -1 over x squared. Okay. Now, on the other side, I can do the exact same thing, and I wind up with the limit as h goes to 0 of, and then I do the same cross multiply trick, but I wind up with x plus h on this side over, and then I've got x times x plus h all over h. Okay. And that becomes the limit as h goes to 0. These x's are going to cancel. I would have wind up with a negative h on the top. And I wind up with an h times an x plus h on the bottom. And I just plug this in, and I wind up with 1 over x times x plus 0, which equals 1 over, sorry, there's a negative there that I lost, 1 over x squared negative. Okay, so they're both about the same for this one. But there are ones that are harder. If I put in cubed or to the fourth, you're going to want to use the h version. If you're doing square roots and cube roots and things like that, you're going to want to probably use the x minus t version. And for stuff like x squared and this, they're kind of a wash up. So 1 to 5, how do we feel about those? Let me check. Okay. All right. And this is a lot of algebra. But the point is, it doesn't really matter which one I use. And by the way, that was a proof. Keep that one in mind because we're going to need it later. But this is actually a proof. Okay. Now, speaking of which, we've got some symbols here. Let's see, it's 803. I need to get through, what else here? Let's skip x cubed. So, did cube root of x by accident. We did that, skipping this one. All right, so we've got this idea. Now, there's two things here, and then I'll get into the notation. There's a way for me to fail to be differentiable. There's actually 3. Okay? How derivatives can fail. Number 1, a discontinuity. Okay? So any type of jump okay? And actually, when we think about it, it's rather obvious that that's going to happen. Because what's going to happen to the slope of this tangent line? On this side, it's going to go into infinity. Okay? So here, if I've got a discontinuity, notice how this tangent line here, right? The secant line here, it goes right? It goes vertical. And I can't do that. Okay? So another term, another way they do it is if they go to infinity. Okay? So if I've got a situation if the derivative goes to infinity, it doesn't exist. Which is related to that one, right? So This one is because of this, but it doesn't, we just categorize them separately because it's easier to think of them like that. And the famous one like this is x is the cube root of x. So if we go back to the cube root of x up here, you'll notice here what happens to this difference function. It goes to infinity, right? So the slope here goes to infinity as I get closer and closer to 0. And we can see that in the formula, right? This thing's got an x on the bottom. So as I go to 0, that thing's going to shoot to infinity, and that's discontinuous at 0. Okay. If the function goes to infinity, it's going to be the same thing. The other way I can have bad things happening to the derivative is if the derivative from the left does not go to the same place as the derivative for the right. Okay, so the derivative from the left and your book doesn't put it in these terms. I actually think these are easier terms to think of it in terms of. It just says the limit. But if the limit from the left of the secant line, which is, harder to say than just the derivative from the left and the derivative from the right, but, whatever. If the limit from the left of this secant thing doesn't equal the limit from the right, so if the derivative from the left does not equal the derivative from the right, this thing's a limit. So if the limit from the left doesn't equal the limit from the right, or the derivative from the left doesn't equal the limit from the right, it's not going to work. And the classic function that looks like this is the absolute value function at 0. Right? Absolute value looks like this. Do a little screenshot action here. This right here is the absolute value. And as you approach 0, oops, there we go. Yeah. As you approach 0 from the left, the slope here is -1. Right? So f prime of 0 left, the slopes from the left here are negative. In fact, they're -1. I can't see it. Okay? But here they're +1. In other words, it's kinky. There's a kink there. So the big thing is that f is kinky. Okay. So the important thing to remember here is that the derivative is an atheistic, prudish white boy. Okay? He's atheistic. He does not like holy or infinite. He's prudish. Does not like kink. And he's a white boy. He can't jump. Okay? And that's what you need to remember. The derivative is an atheistic, prudish white boy. Doesn't like holy, doesn't like infinite, doesn't like things that are kinky. You will not find the derivative hanging out at the Todd on Fletcher in Nebraska. It just doesn't go there. You know, it's strictly meat and potatoes. It likes things to be smooth, not kinky. And you can't jump. Okay, so how do we feel about that, 1 to 5? Okay. Let's get back to this example here. I'm going to go a little bit over time, but I'm okay with that. I know you probably aren't, but, you know, I'm sorry. I'm doing more examples than I normally would. And the cubed one took a thing. So let's do ABS of x at x equals 0. Okay? So let's formalize this. Remember that ABS of x equals negative x if x is less than 0 and x if x is greater than or equal to 0. So it looks like this. That's our glorious absolute value function. All right. So now, if I take f prime of 0 from the left, I get the limit as h goes to 0 from the left of f of x plus h, which is 0 here, f of 0 plus h minus f of 0 all over h, and this is from the left, not the right, which equals the limit as h goes to 0 from the left. Now, f of 0 plus h, this is a 0, right? So it's just f of h minus f of 0. Well, the absolute value of 0 is, well, 0 over h. Now, for this limit sign, I'm less than 0. So I'm going to use this part of the definition. The limit as h goes to 0 from the left. Now I'm going to be using negative x. So f of h is negative h over h, since h is less than 0. All right, well, this is going to cancel to 1. And so this is going to equal the limit as h goes to 0 from the left of negative 1, which equals negative 1 because it's just a constant. Now I do the same thing again. I get the limit as h goes to 0 plus of f of 0 plus h minus f of 0 over h equals, now I'm going to wind up with the limit as h goes to 0 plus f of h minus 0 over h, which equals, now h is greater than 0. So I'm going to use the other definition. So f prime of x and I don't have it, right? And you can see that in this graph. It's kinky. From one direction, it's always -1. From the other direction, it's +1. Here, I've got a kink. How do we feel about that, 1 to 5? All right. It's not a cusp, you traitor. It's a kink. Yeah, some people call it a corner. I think that's boring. I think kink is easier to remember, right? I'm only inappropriate because it helps you remember things. That's not true. I'm inappropriate anyway, but it helps you remember things so I can get away with it. Okay, the different notations. And then I'll do higher derivatives and we'll be quickly. Okay, there are a bunch of different notations. And unfortunately, you just have to remember them. Okay, there's prime notation. So let's see. Let f be a differentiable function. Then f prime of x equals, so y equals f of x. F prime of x equals dy over dx equals y prime equals d over dx of f of x. Let's do this as f of a. All right, so this is f prime of a. Visibly function at x equals a. So this is f prime of a, which is the same as dy dx at x equals a, which is the same as y prime at x equals a, which is the same as d over dx of at x equals a of f of x. Okay? These are all different notations. And I've got f prime of x in general equals dy over dx equals the derivative with respect to x of f of x. Oh, when you thought I was done, right? So, in general, this part here, so in general, f prime of x is prime notation. Dy over dx is Leibniz notation. Oh, I can't spell his name. It's written on the top, but I can't get his name for some reason in my brain. L-E-I. N-I-Z. And d over dx of f of x is operator notation. But wait, there's more. Okay? Let f be differentiable. Okay? Then, and there's more stuff here. This one right here, you also see this a lot. F of x over dx. That's kind of a mix between them. Okay? You also see this. You see f prime. And remember, f is a set. So f prime, this is actually the whole function. Equals df over dx, which is different than dy over dx, equals d over dx of f. Okay. Now, these are the whole set. Well, this usually refers to either the rule or the y value. Why so many? To make you mad. Okay. And one last thing, and I'm only going to mention it at this point, and if it shows up on the test, I will mention it on Wednesday. But higher derivatives. Okay, so f double prime of x equals the derivative of f prime of x equals d squared over dx squared of f of x. So, example. Okay. F triple prime of x is the third derivative. Other notations are also d squared y over dx squared. This would be stuff like is the third derivative, so f double triple prime of x equals the first derivative of f of x, f double prime of x, which equals d squared over dx squared of f prime of x equals d cubed over dx cubed of f of x equals d cubed y over dx cubed. All different notations, and they go on and on and on. After this, we usually put a little parentheses up here, is the fourth derivative, and so forth. Okay. Any questions? 1 to 5, how do we feel about that, if anyone's still watching? Okay. Yep. Okay, so that's just notation. This is just notation. Okay. But you just keep taking the derivative over and over again. Okay, so we ended up doing, let's go through, and then I'll scroll back down in just a moment. So we went over the derivative, the intuition, a different intuition using cost instead. We did a couple of these examples. We did 1 over x as well. We didn't do x cubed. We did do how something could fail to be differentiable. We did all the notations, and then we talked about the higher derivatives. Now, if you have any questions, by the way, that higher derivative stuff is on the book. There are examples in the book. That's in section 2.2. I may have cut it off the problem set because the problem set was running long, but it's one of those things that just looks intimidating, and it isn't. The minute you get the fact that you just keep taking the derivative, you're good. So it's not as bad as it looks on that. And if you have trouble with it, by all means, come talk to me next time. So that's should be all the stuff for test 1. Hopefully. Next time, deriving the power rule. And as I said before, I suggest that you watch that lecture before the test. You don't need to make careful notes about it, but it's got an example, another one of these examples of doing a derivative. So you should, which can help you on the test. Are there any other questions? Okay, so that's it for tonight. Thank you for staying a little longer, and if you have any questions, I'll be around tomorrow morning. Well, no, I won't be around tomorrow morning. Tomorrow's Tuesday. I'll be around on Wednesday. Thank you very much.